Hey guys, in this video we're going to talk about section 4.1 in the textbook. We're going to introduce exponential functions and look at the various parts, and it's just going to be pretty simple introduction. In the next video we're going to talk more about the differences between exponential functions and linear functions, and we're also going to look at their graphs. Okay, so before we start to talk about exponential functions, let's just review percentages. Okay, so if you start with 25 items, how many items will you have after an 80% increase? Well, to do this, you just take 25 and multiply it by 80%, which as a decimal is just 0.8. Okay, and then we get 20. Right? So then we have to take away 20, right? Because that's 80% of 25 is 20. 25 minus 20 equals 5 items. Okay? So after an 80, oh, actually I was supposed to add. This was increase. So let's change that to a plus sign. So we're going to have 45 items after an 80% increase. If it was an 80% decrease, we would have 5. All right, let's do this one right here. If we start with 70 items, how much will we have after a 20% decrease? So this time, we're going to still multiply 20%, which is 0.2, by 70, and we get 14, okay? Then we're going to take 70 and take 14 away from it, and we get 56 items. Okay, so this is just a little refresher on percentages. Okay, so what are exponential functions? So for any given unit of time, the outputs of an exponential function increase or decrease by a certain percentage. Okay, so let's just look at some examples to kind of talk our way through this. So the first example is this. Let's say we have a rabbit farm, and let's say there's 200 rabbits in this farm, and every day the amount of rabbits increases by 10%. So this situation represents an exponential function. And we can actually write out the days. So on day 1 we have 200 rabbits. On day 2, well, we're increasing by 10%. So we have 200 plus 0.10 times 200. So this is 220. So 220 rabbits on day 2, 200 on day 1. On day 3, now we're going to take 10% of 220 and add it to 220. So I have 220 plus 10% of 220. Okay, so on day 3 we have 242 rabbits, and the pattern just keeps going on and on. So this is a situation that can be modeled by an exponential function. Similarly, if something's decreasing by a fixed percentage, that's also going to be modeled by an exponential function. So let's say that we have a certain substance at 300 grams, and it decays or it loses its substance at a rate of 20% per day. So this is also an exponential function, but instead of increasing, we're actually decreasing. So let's kind of draw this out. So this is per day. On day 1, we have 300 grams of that substance. On day 2, it's decreasing by 20% per day. So we're taking 300 and we're taking away 20% of 300. Okay, and let's see what that is. So that's going to give us 240. So you can see that we're decreasing. We're going from 300 on day 1 to 240 on day 2. Day 3, how much are we going to have? Well, we're going to have 240 minus 20% of 240. And we get 192, and this pattern just keeps going on and on and on for each day. Okay, so that's another example of a situation that can be modeled with an exponential function. Okay, so exponential, so as I mentioned before, when something is increasing exponentially, we call it exponential growth. And when something's decreasing exponentially, we call it exponential decay. So in this picture, the blue curve is exponential growth, and we're going to talk more about the graphing aspect of exponential functions in later videos. But the point is that time is usually our x-axis. So as time goes on, as time gets bigger and bigger and bigger, as more time elapses, the function gets higher and higher and higher very quickly. Okay, that's exponential growth when that happens. Contrasting that, exponential decay, here's the start of time. As time goes on, okay, as we move to the right on the time axis, the x-axis, this thing is rapidly decreasing, very fast, okay? So that is exponential growth and decay. Exponential growth is super relevant in our everyday world. The way that the COVID cases grew in 2020 was exponentially. So here we have a graph, daily new confirmed COVID-19 cases. This is after March 1st, 2020. And you can see that, and this is like, you know, for the world, day 0, we have 0. And then by day 25, we have 60,000 new cases, okay? So this is an example of exponential growth, because as time marches on, the numbers for cases get higher and higher and higher very, very quickly. Okay, in just 25 days, we went from 0 to 60,000. It's crazy. So yeah, exponential growth is everywhere. If you are studying to become a nurse, or if you know anyone that's a nurse, the way that certain medicines leave the bloodstream can be modeled with an exponential decay model. So yeah, super relevant, and I'm excited to teach you guys this. So let's go ahead and move on to the actual mathy part of exponential functions. So we have two different equations. We have exponential growth is this equation, okay? And of course, x is our input and y is our output. A and r are numbers. And then we have exponential decay. And notice that the only difference between these two formulas is the plus and the minus sign in the parentheses, okay? So what do these variables represent? A is the initial value. So what does that mean? Well, let's talk about the rabbit example. The initial value is 200 rabbits, okay? So that's what we start out with before it starts increasing or decreasing. A is our initial value. R is going to be the percent rate of change. We can either write it as a decimal or as a percentage. It doesn't matter. In your homework, some of the problems will ask for it to be a decimal, and sometimes it'll ask for a percentage, but when you're actually like writing it in the formula, you want to use a decimal. And then so the growth factor. Now we call it growth even if it's decay, because I don't know why, but 1 plus or minus r is called the growth factor. So either 1 plus r is going to be the growth factor if you're dealing with exponential growth, or 1 minus r is the growth factor if you're dealing with exponential decay. And we're going to do some examples now with that. Okay, so for exponential functions whose percent rate of change is 50%, what is the growth factor? Okay, so this is positive, all right? This is a positive number, even though the plus isn't written, it's understood to be positive. And so the growth factor is going to be 1 plus r, and r is 50%. As a decimal, it's 0.5. So our growth factor is 1 plus 0.5, which is 1.5. So this is our growth factor. Okay. Next one says exponential functions whose percentage rate of change is negative 10%. What is the growth factor? So now we're decreasing by by 10% every unit of time. And so we're going to use the 1 minus r formula because this is decay. We're getting, the number's getting smaller and smaller. So our growth factor is going to be 1 minus 10%, which is 0.10, and that's just going to give us 0.9. So this is our growth factor. And it's actually, a better name would be decay factor, but I don't know, they don't really say that. It's not a common phrase. So anyway, that's the growth factor. And so this is important, these two stars. If the growth factor is between 0 and 1, we have exponential decay. Like this guy, this is 0.9, that number lives between 0 and 1. And if the growth factor is larger than 1, we have exponential growth, such as this first guy. Okay, 1.5 is bigger than 1, so we have exponential growth. So this is decay, and this is exponential growth. Alright, so first, with these examples, we're going to determine whether they're exponential growth or decay. Then we're going to determine the growth factor, our initial value a, and r. Okay, so let's look at number 1. So this guy, maybe we can just write this off to the side. Remember, this is a times 1 plus or minus r to the x, whatever x is. X could be t or it could be another independent variable, but this is our basic exponential function, and depending on whether we're decaying or growing, it's going to be plus or minus r. Okay, so let's look at number 1. So this guy is in the front, so we know that 300 is going to be a, and actually maybe I'll write it down here. A equals 300. That's my starting value, my initial value. Our growth factor is going to be this number in the parentheses, which is 0.6. Now, is this growth or decay? Okay. This is, and actually maybe I'll just do that. This is going to be decay because this growth factor is between 0 and 1. So this is exponential decay. And so now we need to know what r is. Well, since it's decay, we're going to use 1 minus r. 1 minus r is equal to 0.6, and then we solve for r. So basically we just do 1 minus 0.6. At the end of the day, that's what we're doing. So r equals 0.4, which equals 40%. Okay, so this is an exponential decay function. It's decreasing at a rate of 40% per unit of time. So we start at 300, and every unit of time that goes by, our output is going to decrease by 40%. Okay, let's look at number 2. So number 2, our a, again, is just this number that's in the front. So it's 4. Is this growth or decay? Well, this is going to be growth because this is a number bigger than 1. So this is exponential growth. And the growth factor is that number in parentheses, 1.103. And now we can find r. Now, since this is exponential growth, we're using the 1 plus r version. So we have 1 plus r equals 1.103. Solve for r. So basically just subtract 1 from 1.03 to get that r is 0.103, which is equal to, if we move the decimal place, this is just 10, oops, sorry guys. This is just 10.3%. Okay, if we move the decimal 2 to the right. Okay, so that's r, and then we have our growth factor. All right, beautiful. Okay, so let's look at number 3. So number 3, okay, what's our initial value? That's 62, that's that number in front. So a is 62. Is this exponential growth or decay? Well, this number right here is our growth factor. Our growth factor is 0.5. 0.5, 0.5, whatever you want to say. And because that's between 0 and 1, this is going to be exponential decay. So it's going to be decreasing at a constant percentage. Okay, so what is r going to be? Well, since it's decay, we're using the 1 minus r version. Okay, so 1 minus r had better equal 0.5. Solve for r. Basically, we're just doing 1 minus 0.5, which is going to give us 0.5, which is 50%. Okay, so that's r. All right, beautiful. Let's do the last one, and maybe I'm going to do it over here. So our initial value, a, is 2. Our growth factor is 3. Okay. Is this exponential growth or decay? Well, it has to be growth because 3 is bigger than 1, so this is exponential growth. And since that's the case, we're going to use the 1 plus r version to figure out what r is. So 1 plus r is equal to 3. Solve for r by subtracting 1, and that gives us r equals 2. If I move the decimal place 2, if I move the decimal 2 units to the right, I get that r is also 200%. So 2 or 200%. Okay. All right, let's do some word problems. So the initial quantity of a substance at t equals 0 is 118.6, and the quantity is decreasing by 6.7% per year. So we know this is decay right off the bat because it's decreasing. Write a formula for Q as a function of t. So we'll start this off by Q of t equals, right? That's Q as a function of t. Now what's going to go next is our initial value, which we were told is 118.6. The next thing is, well, first of all, our independent variable is t, because that's what it's a function of, t. And then what goes inside is going to be 1 minus r, because we're dealing with decay. Okay? Now, r is 6.7%. But as a decimal, that's 0.067. And that's going to give us 0.933 as our growth factor. Okay, so that's what goes in here. And that's our function. All right. How much of the substance is left after 3 years? So what we're trying to find is Q of 3. Right? We want to figure out how much of this thing is left after 3 years. So we just plug in 3 for our independent variable, which is t. And we can put this in our calculator, and don't forget to do the exponent first. PEMDAS. Okay, times 118.6. So if I round to 2 decimal places, I get 96.32 is our answer here. Okay, let's do some more. So Sperry Glacier in Montana covered about 0.78 kilometers squared in 2015, and it's been shrinking at a rate of 2.8% per year. Okay, so shrinking tells us decay right off the bat. Shrinking. So we want to write a formula for the size of the glacier as a function of years since 2015. And maybe we can call years t. Okay, maybe that can be our variable. So the size is going to be s, and then our independent variable we're calling t. Now, what was the starting amount of the glacier in 2015? Well, it was 0.78, so I'll put that in the front. And t is our variable right here. Now we need to figure out what goes inside the parentheses, what our growth factor is. And so since it's decay, we're going to use the 1 minus r version. So we have 1 minus r equals 2.8%, but I'm going to write 0.028 because we want to write that as a decimal. So basically I'm just doing 1 minus 0.028 when it's all said and done. So r is going to give me 0.972. So that's what goes in here. All right, beautiful. So we have our model for how our glacier is shrinking since 2015 when it starts. Okay, so use the model to predict the size of the glacier in 2025. Well, remember, our starting value happens at 2015. So how much time passes between 2015 and 2025? 10 years, right? So t is going to equal 10. And so we need to figure out what is s of 10. So we're just going to plug 10 into our model for t. And punch this in the calculator and see what happens. So let's see, 10th power times 0.78. Alright, so if I round to 2 decimal places, this is going to be 0.59 kilometers squared is left in 2025. Alright, a population starts with 3 million people, and it grows at a rate of 8% per year. How many people are there after 5 years? Okay, so the first thing we want to do is we want to create a model, an exponential model. And so maybe we can call this P of t for population as a function of time, years. So P of t, we start with 3 million, so that's our initial value. And our variable's t, so I'll put that right there. So what goes on the inside, that's our growth factor. We can find our growth factor with r, which is 8%. Okay, so this is exponential growth because they tell us it's growth, it grows. So we use the 1 plus r version. 1 plus r equals the growth rate, which we need to figure out is right there. Right. Okay. Yeah, okay, perfect. All right, so let's do that. Let's figure out what the growth rate is. So we have 1 plus 0.08, and that's 1.08. So that is what is going to go inside here. All right. And yeah, so that is our model, and now we need to figure out how many people there are going to be after 5 years. So we need to plug 5 in for t. So P of 5 equals 3 times 1.08 to the 5th. Put this in our calculator. Times 3. And then we're going to round because obviously we can't have, you know, we can't have decimals. But let's just say this is about 4.4 million people. Okay. Alright guys, that's the end of this lecture. I hope you learned something, and this is, I hope this is helpful for your homework. I'll see you guys next time. Thanks for watching.